With the hydrogen atom, we have moved into the realm of real systems, and this is evident from all the physical constants that appear in the Hamiltonian, which I've written up here at the top of the page. Now let's examine each of these physical constants and determine what purpose they serve. For example, h bar, which appears here at the very beginning, which is essentially the reduced Planck constant. Remember, it's just h over 2 pi. And this has a value that's given by 1.0545 times 10 to the minus 34 joule seconds. All right, so a very small number, but a very important number, and one that basically tells us something about the scale of things at the atomic level. Now, the second constant that we run into in the Schrödinger equation, or in the Hamiltonian for the hydrogen atom, is the mass of the electron. So let me put this down here. M sub E, which is the electron mass. All right, now obviously it's the smallest mass probably that we'll encounter in this course or other courses. It has a value of 9.109 times 10 to the minus 31 kilograms. Very, very small. Okay, there are more digits for each of these things. I'm just going to give you a few of them. Okay, but the electron mass is something that we can use now to measure masses in kilograms if we wish, but relative to the mass of the electron. Now we have a couple of other constants when we come over to consider the potential for the hydrogen atom. One of those is this E. And this is not the natural logarithm. This is the electron charge. And remember that it's the same as the proton charge, but they differ in their sign. So the magnitude of the electron charge is 1.6021 times 10 to the minus 19 coulombs. Coulomb is an amount of charge that we can measure sort of in a laboratory scale. So it's a very small amount of charge, but we also know it's the smallest whole charge available in any sample of matter. All right, finally, we've got this 4 pi epsilon 0. We haven't talked a lot about that. This is basically the permittivity of the Coulomb force in a vacuum. So we can write this permittivity of Coulomb force in a vacuum. All right, now it's a number that is, again, unfamiliar to us, but we'll go ahead and present it here. It's 1.1, left out a 1126 times 10 to the minus 10, and it has some fairly involved units. It's Coulomb squared per joule meter. Okay, obviously it has to have these units so that this whole term here is in units of energy, or joules. Okay, so when we have these four constants, what does that give us? Well, turns out these are all things that are relatively small, and therefore they are appropriate for things on the atomic scale. So we tend to use these things to define something called atomic units. In other words, if we express things like that are proportional to Planck's constant, which, remember, angular momentum depends on Planck's constant. So this is units of angular momentum. If we express it in units of h bar, then we're expressing something that is in units that are relative to an atomic scale. Similarly, the electron mass, very small. Its mass then can be used to scale all the masses that we might encounter in an atom or a molecule. The electron charge, again, is something that we typically deal with on an atomic scale. So all of these units can be used to define a new set of units, which I'll call atomic units, that are appropriate for an atomic scale. Now, I'll mention that this joule seconds is one that we sometimes might write out in more fundamental units in the metric system. It would be equivalent to kilogram meters squared per second. So I'm going to set this up here just to hold a place. We could similarly do that for the joules down here, but we'll see that it's probably less necessary to do that. Now, once we have defined these four as atomic units, it turns out that we can use these to define just about any other kind of atomic unit. Let me give you an example. Let's suppose we want to define a length scale for atoms. Well, it turns out that if I put these four constants together in the following way, so I'll have h bar squared times this permittivity constant, then divide by the electron charge squared, and divide by the electron mass. Okay, this seems like a rather unwieldy set of constants, but we'll see how this works out. Note that whenever we have the permittivity, we often have the electron squared either in the opposite side, either numerator or denominator, so that we end up with a term that looks like E squared over kappa 0. Okay, that's exactly what we have up here, because when we do that, we're going to be able to cancel these Coulomb squared that appear in the permittivity constant. Okay, so let's see what units we get out of all of this. Now, for the case of h bar squared, I'm going to write this in a very particular way, malice aforethought. Okay, h bar has units of joules times seconds. So I'll leave it as joules times seconds in one instance, but then I'm going to use this other form. So I'll have kilograms meters squared per second as my second form for this. Okay, for the permittivity, I'm going to have Coulomb squared per joule meters. For the 1 over the electron charge squared, I'll have 1 over Coulomb squared. So you can see already the Coulomb squared are going to cancel. And for 1 over the electron mass, I'll have something in units of 1 over kilograms. So now when I go through to figure out all of these units, and we'll cross them out one at a time, okay, I can cross out these joules and these joules. I can cross out these seconds and these seconds. I can cross out this kilogram and this kilogram. I can cross out c squared and this c squared. And then I've got a mass in the denominator and mass squared in the numerator. So this total thing will have units of mass. Okay, so this is one reason why, not units of mass, units of length. This is units of length. Meters. Now, if we were to go through and calculate using the values of all of these constants, we would find that this particular unit of length has the value of, let's put it in red, that's a little more striking, 5.29177 times 10 to the minus 11 meters. Well, does this unit of length have any special purpose, any special definition? It turns out that it does, and it's one that we've already seen. This is simply the Bohr radius, the one that came up a lot when we were doing the calculations on the hydrogen atom. It's essentially the preferred radius for the electron around the hydrogen atom. All right, and it turns out that is naturally what comes about when we use these sets of numbers as our atomic units. Okay, let's do one other example here. I'll try time. Now in this case, what we need to combine in order to get something that looks like time is h bar. We need a kappa 0, the permittivity constant. Again, we need 1 over e squared to get rid of that. And now I'm going to need, it turns out this will give me as something in units of length over time, or I'm sorry, time over length. So I'm going to need to multiply by something with length. And to do that, I'm going to multiply by my new atomic unit here for length. I'm going to multiply it by the Bohr radius. Okay, so when I go through and I figure out the units that I get out of this, h bar will give me joule seconds, kappa will give me Coulomb squared per joule meters. The 1 over electron squared will cancel out the coulombs, and the Bohr radius will give me meters. So as I cancel the like units, I'll cancel meters here, I'll cancel joules here, I'll cancel c squared here, and I'll end up in units of seconds. And so when it turns out when I calculate all this out, the number that I get is 2.4189 times 10 to the minus 17 seconds. Well, that's not a very long time interval. It turns out it's about the period of evolution of an electron around a nucleus in an atom like hydrogen. All right, so it's very, very small number. I'll call that number tau for the electron, or tau for the hydrogen atom, so tau sub h. But this will now form our atomic unit for time. Now we could keep doing this. We've done a couple of very fundamental units because it's useful to have those. The reason it's useful to have them is, let's say, for example, we wanted to do energy. Okay, in the case of energy, we need something, well, we ideally want something in joules, so that means we need to end up with something in kilogram meters squared per second squared. Well, I could get this by simply using my kilograms, which is m sub e, my meters squared, which could be the Bohr radius squared, and second squared, which would be this tau sub h squared. So I could use all of these together now to calculate an energy, and interestingly, it turns out I'll get something that looks like this. I'll get 4.359 times 10 to the minus 18 joules, and this is something that is equivalent to a unit of energy we call the Hartree, and we saw this in the hydrogen atom. So in other words, the hydrogen atom has an energy that's equal to minus 1/2 a Hartree. Okay, we could write this out in these other fundamental units. I've used 2 of our manufactured units to do this. You should be able to show that you would get an equivalent result from this. So in other words, this is naturally arising from our choice of these 4 things as our fundamental basis for atomic units. And we're going to be using atomic units to study larger and more complicated systems because they will make our expressions somewhat more simple without having to carry all these constants around.